Section 7.1, we are going to talk about slope fields. I'm on the second page of the notes for section 7.1, so if you can just forward to that second page. A slope field is a drawing of a differential equation, or a derivative, that will reveal the solution to that differential equation. The solution to a differential equation would be its group of antiderivatives that have that derivative. So let's kind of get started here. I want to make my line thinner. This is going to be challenging for me. I'm only going to do about 3 of these on the first page. The first problem, we have the differential equation dy dx is x plus 1. Each one of the dots on this grid represent a point. So for example, this point up in the upper left hand corner is 3 to the left and 2 up. That represents the point negative 3, 2. dy dx we know means slope. I basically want to draw a slope field showing the slope at each point in this region. Now, the way I do that is I take the coordinates of the point. So this point right here has coordinates negative 3, 2. Now you notice there is no y in this derivative. There's only an x. So the derivative only depends on x. So taking the point negative 3, 2, if I put negative 3 in for x, negative 3 plus 1 is negative 2. I'm going to draw a little line with a slope of negative 2. Now it doesn't have to be perfect, which mine most certainly isn't. But a line of a slope of negative 2 should go down 2 over 1, so it should kind of point in this general direction. Now, moving along, this point is negative 2, 2. So if I put negative 2 in there, now I have a slope of negative 1, so that's less steep than the first one. Then negative 1, 2. Negative 1 plus 1 is 0. That would be horizontal. 0, 2. 0 plus 1 is 1. So now a slope of positive 1. 1, 2. We put x equals 1 in there. We get a slope of 2, and so on. Here x equals 2, so 2 plus 1 is 3. We'll get a slope of 3. Here we'll get a slope of 4. So as we go, the slopes keep getting steeper. And again, it doesn't matter that they're perfectly drawn, just that the ones with bigger slopes are steeper, the ones with a negative slope are negative, and so on. Okay, let's continue drawing. Now what you're going to notice here is that now we're going back over to negative 3. This whole row has an x coordinate of negative 3. So negative 3 plus 1 is negative 2. This whole vertical row, the slopes will all be negative 2. They should be all exactly the same. And I did just a horrible job on that second one. And what I probably should have done is use my line tool for that, but too late now. So all of these have a slope of negative 2. These all have x coordinates of negative 2, every point in this column. So these will all have slopes of negative 1. And again, the important thing, make sure they're less steep and negatively sloping than these. These all have x coordinates of negative 1, so these will all have slopes of 0, and so on. All the vertical rows will be the same all the way down. And why does that happen? Because these derivatives depend only on x. They don't depend on y. So the vertical lines are all the same. Now if you look at this slope field, it appears that the solution is a bunch of parabolas. Now the parabola could be up here, it could be down here, it could be anywhere, but it looks like it follows the path of a parabola. Okay? So the solution, we know the antiderivative of x plus 1 would be 1/2 x squared plus x, and then plus some constant. And that's why we don't know where the parabola is drawn, because it could be shifted up or down any amount, but it has a quadratic solution. Okay? Now, if I look at a slope field or a differential equation that only depends on y, well, now you guessed it, now the horizontal lines will all be the same. So if I start here at negative 3, 2 again, now this derivative does not depend on x, it only depends on y. So a y value of 2 going all the way across, 2 times 2 is 4, these will all have slopes of 4 going all the way across. These points all have y coordinate of 1. 2 times 1 is 2, so these will all have slopes of 2, and I'll kind of start that way. And I'm trying to draw them all the same. Again, my motor skills aren't what they ought to be. Here the y-coordinate is 0, 2 times 0 is 0, so here you won't even see them because they'll be covered up by the axis. These are all horizontal slopes all the way across. Now y is negative, negative 1, 2 times negative 1 is negative 2. So negative 2 all the way across, and then the bottom row, y is negative 2, 2 times negative 2 would be negative 4, so these will be really steep. And there's your equation there. Okay, and to solve this differential equation, you would have to do something called separation of variables, which we don't quite know how to do yet, so I won't talk about the solution to that equation. However, if we would try to draw a solution curve on here, well, if let's say I wanted to go through this point right here, the slope is about like that, but then it levels off here. This must be an asymptote, and then it kind of gets steeper as we go up. Looks like an exponential equation, kind of. Okay, if I had drawn it down here, say through this point, now it approaches an asymptote this way and gets steeper as we go down that way. So it could be, depending on where you draw it, again, you have different looking solution curves. Let's look at one where x and y are both involved. So now if I have this point at negative 3, 2, now the derivative says to add the x and y value. So negative 3 plus 2 is negative 1. Negative 2 plus 2 is 0. Negative 1 plus 2 is positive 1. This is 0, 2, so 0 plus 2 is 2. 1 plus 2 is 3. 2 plus 2 is 4. 3 plus 2 is 5. They become almost vertical. Continue. Negative 3, 1. Negative 3 plus 1 is negative 2. Negative 2 plus 1 is negative 1. Negative 1 plus 1 is 0. 0 plus 1 is 1. 1 plus 1 is 2. 2 plus 1 is 3. 3 plus 1 is 4. Now you start to notice something. If x and y are opposites, negative 2, 2, negative 1, 1, this whole diagonal should be 0. 0, 0. 1 plus negative 1, 2 plus negative 2, those all be 0. You notice along this diagonal, negative 1, 0 is negative 1. 0 plus negative 1 is negative 1. 1 plus negative 2 is negative 1. So you notice the diagonals are the same. These will all be diagonals of 2. Of 1, back to positive 1. This is negative 1 plus 2, 0 plus 1. Here's 1 plus 0. 2 plus negative 1. 3 plus negative 2. Those are all have slopes of 1 coming down. Then all slopes of 2 coming down. Then all slopes of 3 coming down. So they kind of look like that. On this side, same thing. This, negative 3, 1 had a slope of negative 2. This is negative 2, 0. That will also be negative 2. Negative 1 is negative 2. 0 plus negative 2 is negative 2. Then they get steeper. Negative 3 plus 0. Negative 2 plus negative 1. Negative 1 plus negative 2. Then 4. Then negative 5. So they're really quite steep. And one more time, if I would draw a solution curve, let's say through like, I don't know, this point maybe. Now it's flat here, but now it gets steeper and steeper and steeper going this way. And this way it starts to approach an oblique asymptote, a slant asymptote. If I had a point right on this line, now it would just be the line itself at that point. If I had a point here, very steep right here, but then it gets less steep and then approaches this asymptote up here, so you can kind of draw solution curves. So that's what a slope field is, and that's how you draw it. Now, can you match a slope field with the equation the slope field could represent? So up here we have 8 graphs, down here we have 8 equations. Now, first of all, it's easier to match a slope field with the equation it represents because you can just look at the shape. You notice these look like all horizontal lines, so that would look like Number 7, y equals 1. So that's number 7 right there. You can tell these are lines with a slope of 1. That looks like y equals x. That would be 8. This here looks kind of like a cubic, I guess, right? So that would be y equals x cubed. That would be, let's see here, number 10 is 1/6 x cubed. That looks pretty good. Look at this one. It looks like a sine graph. It goes right through the origin like a sine graph, right? So that appears to be number 12. Okay, let's skip that one for a second. Let's go up here. This looks like comes down, then back up. It goes down, then back up. That looks like a cosine graph. So the cosine graph on here would be number 13. Let's see, what does this look like? It comes down, gets flat here, and then goes back up. That looks like a parabola. That would be 9. So what do I have left? 7, 8, 9, 10, 12, and 13. I got 11 and 14 left. 11 is 1 over x squared. 14 is a natural log. Natural log, I guess that would be this one here. We're vertical on this axis, and then it bends off that way. So that looks like the natural log. And then 1 over x squared looks like hyperbolic curves approaching and then kind of leveling off, and approaching and then kind of leveling off there as well. Okay, so that looks like 1 over x squared. That would be number 11. So that's a little easier because you can tell the shape. But what if we had to match slope fields with derivatives? You notice there aren't as many here. Well, some keys to look for. If you look at the equation of number 15, it only involves x. Well, remember, that means all the vertical rows will be the same. So our vertical rows here the same? No, they change. How about here? Yes, these look like they're all the same. Furthermore, if you look here we have x is around -2 right there. If you would put -2 in for x, -1 plus 1 is 0. Anytime x is -2, you can see zeros. So this is almost definitely 15. Number 16 only depends on y, so now horizontal rows should be the same. Not the same there, not the same there. Here they're the same all the way across. This must be number 16. And again, if you look here, when y is 0, I didn't do a very good job there, they're all horizontal. That makes sense. When y is 0, the derivative is 0. When y is 1, the slope is 1. When y is 2, the slope is 2. Okay? Now these two depend on x and y, so they're definitely these. Now one thing you can do is look for zeros. Looks like I have 1, 1 makes 0, 2, 2 makes 0, 3, 3 makes 0, -1, -1, -2, -2, and so on. So what would that be? Well, looks like this one. If I took 1 minus 1, or 2 minus 2, or 3 minus 3, I'm getting 0. So this looks like it would be number 17, because on the line y equals x, I keep getting 0, and that would happen in this one. So by default, this has to be 18. Let's see here. I've got all zeros on both the x-axis and the y-axis. Whenever x is 0, I get 0, so that makes sense. Those are all horizontal there. When y is 0, it's undefined. So when y is 0, they don't have any slopes drawn at all. Okay. Other things, notice where it's positive. Everything in the first quadrant has a negative slope. So when x and y are positive, this is negative. That makes sense. Everything in the second quadrant has positive slopes. So a negative x and a positive y, negative x and a positive y would be a negative, and then the negative in front, yep, that makes those all positive. Okay. So the rest of this stuff is all kind of similar questions. Here, they're going to ask you to sketch a solution curve through the point 0, 1. So you find 0, 1, and you say, okay, the slope's about like that there, but then it gets steeper as we go this way, and then it levels off there, but then it kind of approaches an asymptote there. So you're just drawing solution curves over it, okay? We're going to come back and we're going to talk about how to solve some different differential equations and what it means to solve them, and we'll go from there.